Guys, enjoy your presentation. Any questions you might have, again, please post them in the Q&A box. I'll be sure to answer them or ask Rob to answer them for you. Thank you so much, guys. I hope you enjoy.
Okay, thank you, Tepi. Hopefully at the end of this presentation, we'll gain some more information. So my name's Rob. I'm based here in Perth in Western Australia. I've got some takeaways from this one. I think at the end, if we can consider that when you're designing a system, look at some of the risk analysis and likely places for failures to ensure your system is resilient. Have a bit of an understanding too that we're excited about the way technology is going, particularly with space communications, internet everywhere, but just understand that it may come at a cost to society for this desire of 100% data coverage. And also the other thing is to look at the impact of malicious damage by hostile governments, hostile agents who deliberately are trying to sabotage some of our systems. Now, that's the takeaways. So a little bit about me. My name's Rob Howes, as I said, based here in Perth in Western Australia, been here most of my career. I hold a diploma in electronic engineering, a master's of technology management, and I'm a Prince 2 project manager practitioner. My career has been in civil aviation, in navigational systems, radars, instrument landing systems, everything associated with that, as well as an extensive career in satellite communications. My current role is with the Curtin University Radio Astronomy Department as the project manager to deliver a space domain awareness radar system. So we'll talk a little bit about that a little bit later on. When I was asked to do this presentation, I was trying to think of a topic that I'm passionate about, and the resilience of the reliability of a design system is fairly critical. And a perfect segue occurred about 3 weeks ago that allowed me to talk about this in depth, and that was the CrowdStrike incident, where just about every computer in the world was impacted by a software glitch in a company that was trying to improve the security of the system. So this was the headlines of our local newspaper, the West Australian. The computer says no. So I thought that was a good segue into what I want to talk about. Of course, the impact of something like the CrowdStrike would be depending where the system is deployed. Some people it was just inconvenient. But in this case, this is a navigational system on a private aircraft. This plane isn't going anywhere today because of an external factor that wasn't considered. Just want to talk briefly to start off with this one about reliability. We talk about reliability. A lot of contracts talk about 5 nines reliability. So this is a system that has been designed and will be up for 99.99% of the time. So I've seen so many contracts that talk about this 5 nines reliability, and everyone goes, yes, we can do that. But what does it actually mean? So just as a bit of a chart here, we talk about 90% reliability. That means the system can be unavailable for 36.5 days a year. That's over a month a year if it's only 90% reliable. And we go down that until we get to the 5 nines, which means that the downtime is only for 5.5 minutes a year, about 45 seconds a month. We'll talk a little bit later on. So just a quick maths for anyone that I may have lost, but if you want to calculate downtime, you just take the uptime. So if you've got 90% uptime, subtract it from 100, multiply the number of days a year, divide by 100. So for 90% uptime, means you've got 10% downtime, multiplied by 365 days of the year, means that your downtime, your acceptable time the system can be down for, is 36.5 days. So again, applying those maths to the 5 nines, the 99.999, the downtime comes down to 45 seconds a month. This typically allows you probably to switch over to the backup system. in designing the systems, you've got to make sure that if this is what you're aiming for, that the backup systems will come up in that time. I've seen systems where they all share common data storage. At the time it takes to switch over will exceed this. So in your design of your system, you've got to consider how I'm going to deal with system failures. So things that impact on system availability, I think most of us can list some of those. Human error, oops, I didn't mean to do that. We can have machine failures, actual hardware failures. We can have deliberate attacks, which can be a cyber attack, mainly around software-based type systems. We can have a physical attack. So an example from some time ago, somebody decided that they didn't like our telephone system in Sydney, and they jumped into the pit with an axe and cut all the cables. So that was a physical attack on the system. The impact it had on society was fairly significant. And that still can play out nowadays. We have cases where farmers, agricultural workers, that, not picking on them as a group in particular, but they may put a post hole digger through the optic fibre cable, which will impact significantly on your communication systems. We'll have weather events can impact on your system. They can be things like floods, but I want to talk a little bit more about weather events later on in this presentation. You run out of spares. I've seen this often with a lot of legacy equipment. There's just no spares. Your system fails, you can't recover it, the spare system is broken. You really need to decide when am I going to replace that system, and hopefully before it fails. And of course, that has the financial concerns. You know, do we have money to provide services? And that I've been involved in a lot of radio communication networks where, particularly for emergency services, so they want their system back up quickly. So just having staff available to recognise a failure and correct it can be a financial concern, because you've got to pay overtime and penalty rates and all that sort of thing for just staff to be there. So that can have a huge impact on your system availability. We can look at some of the external sources, and this presentation is probably a little bit more around about the external things, but simple things like power, cooling systems, particularly if it's a nuclear power station, you've got big issues there. The big ones for me in this takeaway for this presentation is around the communication systems. This the system interconnection where we share data, and it's a critical component of your system to design is to share data between other systems. And very much reliant now on our systems to use satellite-based GPS timings and synchronization signals. So a lot of systems I see being installed now rely on external timing systems from the GPS satellites. It's convenient. It's now become a very cheap method of getting timing. But you've got to consider what's going to happen when those signals go away. Should they go away? What's my backup? Previously, I've installed systems where we have internal accurate timing systems, and normally backed up with a redundant system as well. So again, in consideration, go, well, what will happen if my GPS signal goes? What will happen to the system, and how can I test for that? The thing that often gets us is that events happen that we didn't think were going to happen. So these are known as black swan events. These are a metaphor that describes an event that gets us by surprise. It has a major impact on it and is inappropriately rationalized after the fact with the benefit of hindsight. We go, oh, yes, we could see that happening, but we didn't see it happening. So a data breach would be one. The failure of implementing a software change can be described as a black swan event and should be considered. Often the event is a surprise, and it has a significant impact. And once it's happened once, we tend to rationalize it and go, oh, well, we can deal with it next time, but we're caught out in the first time. And I think we can all think of an event that has happened. As I said, I'm the project manager to build a passive radar to track objects in the low Earth orbit. So space domain awareness is the study and monitoring of satellites and other items in the Earth's orbit. These objects comprise of active and deactivated satellites, spent rocket components, and fragmentation debris. Sadly, it's growing daily. In particular of interest is we've got three predominant orbits. We have the low Earth orbit, which is the first 2,000 kilometres. My project's considering looking into that low Earth orbit. So in the low Earth orbit, we've got the International Space Station and the Hubble telescope, probably two ones that we know about, but a lot of communications and other scientific satellites, some of the weather satellites that are in the LEO, and Starlink typically runs around in the LEO orbit. So the first 2,000 kilometres from here to Earth. After that, you go into the GEO orbit and then into the mid orbit. So GEO's normally out to about 15,000 kilometres. A lot of communication satellites out there giving worldwide coverage. In the medium Earth orbit, you'll find the GPS satellites. So they're the three bands, but in my case, I'm particularly interested in the low Earth orbit. So I just want to talk about the space race and how come we're doing things in space. So back in the 4th of October in 1957, the Soviet Union launched this first artificial satellite called Sputnik 1. And this was probably the go flag on the space race. So that was back in 57. But when they launched the Sputnik 1, it was described as a surprise to the Americans. They didn't expect this happening. They were concerned that the Soviet Union at that stage was ahead of them, so they're getting quite excited about what's happening, and a lot of money and time was put towards the catching up. But very soon, within hours of launching Sputnik 1, two American physicists at the Johns Hopkins University of Applied Physics decided to monitor that. And they realized that a thing called Doppler shift, they could pinpoint exactly where the satellite was in its orbit. And Doppler shift, this is where the frequency changes according to whether the item is approaching you or going away. And you can demonstrate this quite simply. If somebody's sounding a car horn while driving towards you, you can hear it increase in frequency, or as it's going away from you, you can hear it decreasing in frequency. And just quite simply, you can work out whether the car's coming towards you or going away you based on the change in frequency. So that's Doppler shift, and my project uses Doppler shift to determine the position of objects in space. So anyway, we had the Russians launch their satellite. The United States wanted to catch up quickly. They had a few objects to put in space, but in July 1962, they launched the first commercial satellite with a commercial payload, and this provided television broadcast. So that was known as Telstar 1. Telstar 1 operated for 7 months before it succumbed to damage. For some reason, deliberate or accidental, they launched the satellite through a high altitude nuclear explosion, which is part of the Starfish Prime project, which damaged the electronics in it. Although the satellite is not functioning, ceased functioning, as I said, within the 7 months, they launched Telstar 2, which took over its services. The thing is that Telstar 1, launched in 1962, is still in space as space debris. In 1978, a NASA scientist, Donald Kessler, put a proposition forward that if two colliding objects in space collide, they'll generate a lot of debris, or generate debris. That debris will collide with other objects and create more shrapnel and litter until the whole of the low Earth orbit is impassable, rendering the region unusable for reliant space use. So that was 1978, Kessler's effect, and it's actually gained a lot of traction. The thing is that it may damage existing infrastructure if this does happen. It may also prohibit the launch of other satellites and launching through into interstellar travel because you've got to get through this debris. And you may have, if you watch any of the launches, you'll see that they'll actually talk about space debris avoidance in their launch windows. So just going in with a space domain awareness, as I said, this is my project. Just trying to get these slides to. So there's a number of ways to determine what's out in space to track them under the space domain awareness. You can just use an optical telescope and look at the items. You can use lasers. You can use an active radar system. So there's a company called Leo Labs that have got an active radar system. They transmit from an antenna and receive it on two adjacent receive antennas each side of it. This gives them the ability to determine the speed, direction, size, and trajectory of the item. You can do it as my project's working on, the passive radar system. We don't actually have a transmitter. We rely on third-party transmitters, and these typically are FM radio stations, television transmissions, those things in the 80 to 250 megahertz range. These signals from the television station will go through space, up through the ionosphere and continue in space. If they hit something, we detect it. We know where the transmission came from, so from the be it the FM radio station or television station. By looking at the Doppler shift between a number of receiving points, we can determine the location of the item. So that's called passive radar. And the fifth technology is using passive RF, where you can look at the transmissions, not the link transmissions, not the one carrying the data, but you can look at the telemetry link. All the satellites up there will relay information. So from that, again, not decoding it, but just knowing where it is, you're looking at the signal, you can determine where the item is. So that's the five technologies. And for space domain awareness, the typical approach is to see a number of items. So, for instance, recently there was a problem with one of the Starlink satellites that was tumbling, that type of thing, and they didn't know what satellite it was. We could see that it's tumbling. We went to the optical telescope operator, and they determined that the item, they could physically see what the item is and determine the true identity of the payload. My project involves in-house development and manufacturing custom-made passive radar equipment. So I describe my job as a professional hobbyist. So an exciting field to be in, but it is becoming quite a area of interest around about what we're doing in space. And there we are. That's just one of the 512 antennas that make up my system. Exciting until you actually got to put them all together and cable them all up. So let's have a look a bit of more about the space debris. So there are, as I said, there's active satellites up, but there's a lot of space debris. So back in about 2022, a Russian rocket motor exploded and released hazardous debris in fragment form, and polluted part of the LEO orbit. The engine parts are up there at the moment. They will re-enter. A lot of the stuff will burn up, but typically it will take between 5 and 25 years for the items to re-enter back in the atmosphere and burn up. So the international convention now is to place disused satellites and components into the orbit where they'll deorbit in 5 years. Problem is that is in the lower LEO orbit, which means that it's taking up room where we want to launch through. So it's quite a complex issue. Just as a quick snapshot, what's up in LEO, what we've done since 1957. Currently, there's approximately 200 active satellites in the Earth's orbit. There's about 3,000 dead satellites in the Earth orbits. There's 34,000 pieces of space junk greater than 10 centimeters. There's 128 million pieces of space junk larger than 1 millimeter. And we've got a 1 in 10,000 risk of collision. To avoid the collision, to undertake a debris avoidance maneuver. And of course, every time you do that, you use up fuel, and space fuel is rather a precious commodity because that determines your life expectancy of your satellite. Just out of interest, the International Space Station has had at least 25 debris avoidance maneuvers since 1999. So they're constantly monitoring what's happening there and undertaking maneuvers. There are some companies that are looking at ways of cleaning space up, various techniques. Gravity is our friend, or lack of gravity is our friend up there, so they can use nets. There's ideas of dispensing iron filings to deorbit these items. There's basically like a giant vacuum cleaner to go through, but a costly exercise, but it's going to become more and more important. Just out of interest, what else is floating up in space? We've got a glove from astronaut Ed White, who did the first American spacewalk. He's lost a glove. That's floating up there. There's a camera from the Gemini 10 project, and another one was lost during one of the shuttle spacewalks. There's a thermal blanket floating around up there, and this one's a little bit more scary. Russia put up at the Mir space station. It had a 15-year life, and they would jettison their garbage into space. So we've got bags of frozen waste, and unfortunately, a bit of frozen human waste included in that. By the way, there's a toothbrush up there, a pair of pliers, spanner, and somebody lost a briefcase-sized tool bag. So these are all floating around in space, and they're moving around about 10 times the speed of a bullet. So if they hit something, you've got a problem. We also, not only the space debris we put up there, but there's micrometeorites. So this is the damage done by a micrometeorite. This is something around about 1 or 2 millimeters in size, due to its velocity, hit the front screen of the Space Shuttle Challenger. The good thing is that their windscreens were 6 layers thick, but you can see the damage, and that was just from something around about the size of a ball bearing. What's happening in the future? We've all got excited about SpaceX and putting global coverage of satellite systems in there. We're seeing expansion programs by a number of private organizations, SpaceX, Amazon, some governments are also looking at it. And if successful, they could be adding another 50,000 satellites into the low Earth orbit. So that's going to increase the desire for making sure that we don't lose our space-based assets, in particular those that provide communications and navigational systems. There's also a risk that foreign agents, hostile countries, whatever you would like to put that title to, may damage satellites deliberately for gain. A number of countries have destroyed satellites using lasers to see whether they could do it from a ground-based laser or a space-based laser, and that just contributes more to space debris. So consider that, you know, while it's exciting about having your internet available around the world, there is a significant constellation of satellites up there supplying that, which may be at risk. The other thing I'd like to just touch on is space weather. So this is just like our planetary weather. This is what's happening in space, particularly around solar activities. So space weather refers to events beyond the Earth's atmosphere which impact upon our technology and near-Earth space environment, again, the LEO orbit. The primary sources of this space weather is the sun, and the greatest disturbances usually occur during solar flares, and the solar flares generate a geomagnetic storm. These storms can impact on technology in the near-Earth space orbit, including satellites, terrestrial communication systems, power grids, and aviation services. There's an event that occurred back in 1859, known as the Carrington event. And anyone that speaks about space weather will refer to the Carrington event. So back in September that year, at that stage, communication was primitive by our standards now, and a lot of the work was communication was done by Morse code and telegraph. The operators reported they were receiving electric shocks, that telegraph paper caught on fire, and they even reported the ability to operate the equipment without the batteries. So this was a result of a solar flare. Prior to the event, the aurora borealis, which is known as the northern lights, we also see the southern lights, was visible at much lower latitude. So we've seen this both currently. We've seen a number of these polar lights shows. They're fantastic. They're super brilliant. They're exciting to watch. But we're being able to see those, in our case, we can see them from Perth, where typically we'd only see them in the lower regions of the planet. So that's looking at, so that's the Carrington effect in 1859. In May 1921, this is the New York rail incident. So the entire signal and switching system of the New York Central Railroad was put out of operation following a fire in the control tower on the 57th Street and Park Avenue center. It was attributed to, this fire was attributed to that the the voltage is induced in the teletype system, and the reporter, one of the operators, reported that he saw flames coming out of his instrument, engulfed his switchboard and leading to the fire. This took out the complete rail signaling network for New York, but it has also caused impact on a fledgling telephone system in Europe and other systems. The railroad officials officially blamed the fire to be caused by a solar storm. And as I said, in Sweden, the telephone storm station was burnt out, and the storm interfered with telephone, telegraph, and cable traffic over most of Europe. These events typically run for about two or 3 days. But if you've, but that's for the actual event itself. The consequences of those events, such as rebuilding the damaged infrastructure, can go into weeks, months, if not years. Closer to home, May this year, we had a storm. The good thing is about it, there's a number of solar observatories that talks about, we knew it was coming. You know, we knew it was going to happen, and a lot of companies could actually do something about that were once they were made aware of it. So we saw some of the power companies turning off its long transmission grids. Most transmission systems have capacitor banks in them to balance out the system. They open those up so that they wouldn't store the energy. So we were prepared for that one, but there were some impact on it. So some of the GPS guided farm equipment, with one reported that the storm had impacted on the GPS signal, and his tractor just went berserk and drove around in circles. Other things that were required, the space station astronauts who on the ISIS were advised to avoid areas where protection were low, because you've got this massive surge. So they avoided places like the airlocks. We saw airline operators avoiding the Earth poles so that we wouldn't be subjected passengers and crews to spikes in cosmic radiation. So we knew about it, we made some plans about it. When we talk about these solar storms and the impact on our society, solar storms are typically measured in nanoteslas, which is with a baseline measurement of a non-event day around about 20 nanoteslas. The storm that occurred in May this year was 420 nanoteslas. So we saw some damage to GPS, disruption to GPS signals. We saw disruption to HF communications and things like that. The New York rail storm of 1921 was about double that, so around about 900 nanoteslas. And scaringly, the Carrington event of 1859 was likely to be around about double that again, about 1750 nanoteslas. So obviously back in 1959, we didn't have the instrumentation to measure interference, but it's been estimated that that was about the intensity which did that damage. So the big question comes to is if we had a solar event equal to the 1859 event today, what would it do? So we're looking at something that was 4 times greater than the one in May this year. So we'd probably lose internet services. Other communication systems would fail to communicate with each other. We'd lose high frequency communication such as air grounds, shortwave, ship to shore radios would be disrupted. We would see damage to power transmission systems. There is a risk that satellites in orbit around the Earth could be damaged by induced currents from the geomagnetic storm, just basically burning out their printed circuit boards, and which would result in long-term disruptions to satellite-based telephone, internet, radio, and television, as well as GPS systems. So a bit scary if we have something equivalent to the Carrington event. So we would see that it would be more than just telegraph wires. We would see that just about everyone on Earth would be impacted as we see damage to electrical systems. And as we're saying, we've got more and more ever-growing dependency on technology, and it impacts on things like finance, communications. Just as a personal thing, during the recent cyber incident, the banking system here in Australia was disrupted. You couldn't make purchases at shops unless you had cash. So I know personally, I was sitting in a store to buy a bottle of wine for dinner, and they said cash only. So I'm trying to eke out enough money to buy a bottle of wine. So if you look at the impact on society, there is a significant event, and this is from an event that we cannot control. There's another effect of these geometric storms. They actually cause a change in the density of the atmosphere where the satellites orbit. So it actually gets greater density, and this can drag a satellite out of orbit. And if it's not maneuvered back into orbit, there is a potential that it could fall back to Earth, or, because it's out of control, collide with other space objects, which would lead to its damage. I know that Starlink, during one of these events, lost about 35 of the satellites because they were in a lower orbit. The density of the ionosphere caused these things to fail. Who knows about space weather? Here in Australia, we have the Australian Space Weather Forecasting Centre. A lot of their data they get from a satellite that's based in the Lagrange orbit, just between the Earth and the Sun, feeding back about the likelihood of events that are occurring on the Sun that could impact on us. We get about a 2 to 5 minute warning on what's going to happen. So you've got to be prepared to react to that in those timeframes, and a number of government agencies do. So this is if you go to the Bureau of Meteorology's website, look up space weather, you can see all the information about what's happening in space weather. So there's agencies all around the world doing this, and they obviously communicate with each other. But we can see a preamble into what's going to happen with the space weather event a few days out, and just watching it and knowing when the peak is going to come. Power transmission companies are very interested in these events. Aviation and space agencies are very, very keen about this, knowing what's happening. So I've sort of got to the end of my passionate part about what we're doing in space with our space debris, and also things that we can't control, which is is space weather, but we need to be able to include this in our systems and understand what we can do. So when we're designing a system, one of the things we should do is have that open questioning type environment. What's going to happen? What can we do? What can happen? How will my system work if we lose the timing on it? How will my system work if we lose communications? How do we back things up? Data, so we don't lose all our data. So for those that have studied project management and engineering management, there's typically 4 stages, and each stage we should look at this failure analysis. So factory acceptance testing, we've cobbled everything together, put everything together, and testing to see whether it works in isolation. And then we're going to do some integration testing, because we're now going to integrate our new system into typically a legacy system that we've had for a while, and then we've got to ask those questions again. What happens if I lose my timing? What is the impact of losing my communications? What happens if we lose power? How does the system respond to a power failure? How do we back that all up? And then we then typically deploy it to site. So again, we go through the same process, the site acceptance testing, the site integration testing. And again, test your failure modes. Test, again, the loss of timing, the loss of communication, the loss of power, all those sort of things, and see how the system reacts. And obviously develop a plan of attack. That's probably the best way to describe it. And I'll understand that some of these damages that can be done to the system are not accidents. They are intentional cyber attacks or physical destruction of systems by people for either just wanton destruction, accidental, or a deliberate I'm trying to avoid saying the act of war, but how does your system rely on those sort of factors, and how do you minimize the impact on and based on the importance of the system? Just a little side note here that, and I've seen this many times, is that when we're integrating a new design system with all these bells and whistles, we normally put it into an old system. We link it up to an older system, which may have limited spares or be susceptible to electrostatic discharge damage. While you might go, oh, we don't need that for this reason on the new equipment, but you're going into old equipment, and particularly where there's no spares. And I've seen this where integrating systems into rail signaling systems, we've taken this brand new system that does all sorts of exciting things there, and we're putting back in, connecting it to a system that was designed and built in the 70s, which has limited sparing, there's no sparing available, and also doesn't like static discharge. So at this stage, I said I would do 45 minutes, and I'm pretty close to actually getting it. But just remember that risk cannot be transferred. You'll always own the risk. It doesn't matter what it is. You are the owner of the risk, and you must be key in ensuring that any potential threats are addressed. I mean, you may be able to insure against losses, except that's getting harder and harder, but the risk of the system failure still exists, and you're responsible for that. So just bear that in mind and go, oh, it's all right, it's somebody else's. I have seen this time and time again when I've talked to people about system failures and potential system failures. A lot of it around lightning protection in systems, and they said, they just said, oh, the system belongs to somebody else, it's not my problem. They're the end user of the system, and they are responsible. Anyway, I think that's about it. Thank you very much, and hopefully out of this you'll consider that you need to do some sort of risk analysis when designing a system around external failures to the system. And just think about when you get excited about being able to share your barbecue lunch in the middle of the bush through a space satellite system, that the systems that are bringing you are getting more and more cluttered particularly in the LEO orbit. And also understand that malicious damage to systems can be there. That comes down to both physical and data security, because some of these can be geopolitical, which means just a foreign agent deliberately trying to disrupt society, your society. I trust that this has been informative, and I do thank you for your attention for the last 45 minutes. And I don't know, do we have any questions?
Hi, Rob. We sure do have some questions. So I'll start off to say that the questions, the ones that we'll start off with, are in the Q&A section. So I'll just read them to you, and then you can possibly answer the questions. And then once you are finished, I will continue with the presentation regarding the courses that EIT offers that cover this topic. So our first question is, just a moment, please. The first question that we have is from a gentleman who is currently based in Ghana, and he would like to find out, as an electrical engineering professional, how do you achieve communication system redundancy as a contingent for any communication system failure? So communication from ISS to Earth station and vice versa. This is from Napoleon.
Okay, I understand your question, Napoleon. I mean, redundant systems need to be just that, redundant. They cannot use the same infrastructure. Often you'll find that systems, redundant systems, may be of a slower data link or a more essential link. So if you're talking about the International Space Station, it would be alternate frequencies and alternate modes of transmission. So instead of being high-speed data, it may be voice links and all that sort of thing. So I'm not too sure whether that's answered your question, but then I think the thing is you need to understand what some of your options are, and also look at older systems. You know, don't always rely on the more high speed, exciting type ones. Just as a quick footnote to that, I'm also a volunteer with a group called the State Emergency Service. So we're volunteers that provide emergency response. I'm in the communications support unit, and we actually have trailer mounted communication links that we go out and in a disaster or an emergency bushfire response or a flood or something like that, we take these out to supplement the existing communication systems. The other thing to understand too is that, you know, a lot of people are very, very reliant on mobile phones, but in emergency situations, the mobile phone towers tend to get overloaded, particularly when people are transmitting lots of data, so a lot of video files and that sort of thing, and can't be reliant on being used in an emergency one. So I trust, Napoleon, that's answered your question, at least given some food for thought.
So the second question we have is from Daryl, and he asks, what strategies do you find most effective in enhancing the resilience of engineering projects, especially in the face of unexpected changes or challenges?
That's an interesting question. My first thing is that keep it simple in designing your system. You know, so often we get excited about making a very exciting, flashy type system. Give you where I'm sort of heading with that is that during the space race, the Americans spent millions of dollars in trying to design a pen that would work in zero gravity upside down. The Russians used a pencil. So, you know, that's about keeping it simple. So in your designs, look at true and tried systems, look at simple systems, and look at systems that can be repaired easily without any unnecessary complexity in their design. So I trust that's answered your question, Daryl.
We have another one from Daniel, and he says he's a mining engineer based in Ghana, and he'd like to hear your thoughts regarding the future of space mining.
Oh, a little out of my field. Depends what we run out on Earth that's in space. I know that, interesting enough, one of the things about the spent products in space, there are companies looking at recovering those for mining activities in terms of being able to recover precious metals and things like that. So it's the value in the item that they want to get back. But space mining, I mean, I know that a lot of these thoughts around space mining was purely to be able to get products to continue your space journey. So you'll go to the moon, you'll mine products to use that as fuel, and that's going on. Personally, and this is my own personal view, I think space mining is a very futuristic, wishful thinking, and probably won't see in my lifetime because of the costs associated with it.
So we have another one from HT, and he says, very interested in hearing more about the loss of 35 Starlink. What was the monetary cost, and has there been future risk mitigation planning, as there are some national governments dependent on the service, so the Ukraine and Tonga, and what does this mean for the future of their national security?
Okay, so probably one of the things I suggest is to go to our friend Google. We'll talk and pose those questions to Google. Yes, they learnt the lessons. Some of it comes around to timing. And again, it's this risk analysis to see what's happening and taking data from the National Weather Space Weather Ones to see what's happening. They have relocated their satellites in a higher orbit to avoid that, but let's just say it was a lessons learned, and they will mitigate that, because I can't talk about financial loss, because financial loss doesn't necessarily mean the loss of infrastructure or the hardware. It is also the impact of the loss of the data and the use of that service, which comes into the financial impact. But as I said, have a look on the internet, and they'll tell you how they mitigated it. And when you look at it in percentage, 35 satellites amongst a couple of thousand is only a very, very small percentage, and there is sufficient redundancy in their network for these contingencies.
And then a couple of more to go. HT also says, do you have a term for geopolitical risk beyond the nation state? Is it existential?
That's a deep philosophical question. But when we're looking at trying to gain benefit in a conflict, then anything will be considered. So I'd have to look at a few dictionary definitions to give you a more exact answer to that. But as it is becoming more prevalent, the use of warfare within space is a significant consideration now. And again, if you go into a number of the commentators on the internet, they'll talk about what some governments are doing, what foreign agents are doing in terms of debilitating nations. Not sort of getting involved in warfare and that, but if you can invade a country and keep the infrastructure intact, that is a win. So if you can only disable communication networks and that sort of thing, it makes a desirable outcome for war. Don't agree with war, but anyway, we'll leave it at that.
Okay, guys, I'm going to close the Q&A portion. I'm just going to go over the last few questions. I won't be taking any more question after Lee Marvin. And then we have another question from a participant, and he asked, Southwest had their system online, but due to their other connected system failure, the system failed. So my question is, all resilience or resilient should be of the same type. I'm not sure if I pronounced the word correctly. In case of any changes in local law, how can resilient systems be taking part?
There's a number of sections in that question. I can only talk about sort of the engineering side of things, and that's that often if you've got there is a difference between a standby system and a backup system. So a standby system is one of equal capability and a backup system is one that will provide probably a reduced service. So in resilience, it depends on what your network is and what you're trying to do in your communications network. You know, what is important? Is it just to have basic communications? Is it providing a heartbeat for your synchronization, that sort of thing? Then you can go to a backup system of a lower speed. I mean, often in communication system is to have redundant paths. So one may be a satellite-based system, that may be your backup system compared to an optic fiber landline. The backup to the optic fiber line may be a copper line, but dual path, so that they both don't, you know, if you're losing, I've seen this with optic fiber systems, they have put them on each side of the road to give them redundancy, but they share the same bridge when they go over a river. So a loss of the bridge will lose both the primary and the redundant system. So you want to have a system that takes an alternative route or a backup type network which uses a lower speed, more. I mean, you can go back to the good old days of where we used to use troposcatter links, which didn't rely on terrestrial infrastructure, but wasn't such high capacity.
Three more questions to go. May I ask if there are any responses targeting the control of the amount of debris that is lost, of lost satellites rather, in space?
There is, unfortunately, no one owns space. There's not a. It's by convention that nations are share it. Those that are of a nice nations type things have got decrees, things like you'll set your system up to deorbit in 5 years, not in 25 years. There'll be an understanding of launching. I have heard there's discussions around mandating that you will recover your system within a certain time frame, or I've even heard systems where, you know, for every bit you put up in space, you bring 2 bits back as sort of like a recycling can approach. But space is now a requirement to be cooperative, but there are too many people in the question. There's not a single controlling agent, and even if you go to the international court to get things done, it's a very time consuming one. So I think the answer is until we can come to a conclusive agreement who owns space or controls space, we'll start seeing not nice things happening. As I said, you know, we've seen countries blow up a satellite to test their capability. That's led to space debris. No one can stop them.
So this is our last, I shouldn't say question because there's 3 of them in his paragraph. But Lee is asking, why is resilience important in engineering design and development?
Oh, no, I was going to wait for all 3 questions. No one else wants to design a system where it will fail. I think as engineers, we're always excited about building something that's going to last. So when you're designing that system, you've got to look at all the possible modes of failure and try and engineer those out when designing the system. Obviously, there'll be factors associated with that one, which will be cost. Quite often in our current commercial world, time to market is very important for people. You know, they need to get things into the market before their competitor does. So there's lots of non-engineering factors in it, but as an engineer, I would always like to think that my system's going to work, it's going to be beneficial, and it's going to last within the expected life expectancy of the item. So probably a very quick analogy would be when we go buy a car, we expect it to last between 10 and 15 years. We don't expect to buy a car and knowing that it's going to fail in 2 or 3 years. So if you apply those sort of, yet we don't expect a car to last 50 years. So we have a time frame around it.
Second last question. How can engineering projects be designed to withstand and recover from disruptions?
that comes back to the whole theme of the topic, which is about risk analysis. So you've got to understand what your system is, where it's placed, and what its external requirements for it to operate at. And look at those and go, what is going to be the impact on my system if I lose an external input, or in some cases, we can't get spare parts for it, that type of thing. So it's very important to make sure that you understand the environment designing, and this can be a simple system, which might be just in a domestic environment, or it can be a component of a major system. So communication network is a major complex system, and you've got to understand where your system fits into that and the importance that your system plays in providing downstream services.
So your last question for the day, this one is still from Lee, and his last question is, how can risk assessment and management strategies enhance the project?
I think when you, any project you start, you've got to do a risk assessment. Anyone that starts a project without any form of risk assessment is doomed for failure. Now, those risk assessments can be either based around your hardware, software design of the system. It can be around marketing. Who's going to buy my system? What is the competitors? Those that want to look at that environment should look at Porter's 5 forces models. Where my system's going to sit in, and how it's going to interact. So, if you're not doing a risk assessment at the start of the project, then you're running a risk of a failed project.
That's it for today for your portion, Rob. Thank you so much for joining us today. We do hope to see you on our next webinar. We have quite a lot set up for the year, so hopefully you will return to present to our prospects once more. Thank you.
Thank you very much, Debbie.
Okay, guys, I'm going to reshare my screen so that we can get to the information regarding how to request for your certificate of attendance, as well as the courses the topic that we have today that include this particular subject. So just a moment, I'll share my screen with you guys. So what courses cover this topic at the Engineering Institute of Technology? We have an advanced diploma in industrial data communication, networking and IT. The program is 18 months and it is fully online. We also do offer a professional certificate of competency in project management for engineers and technicians, another advanced diploma in electrical engineering, electrical systems, and then we also have a diploma and an advanced diploma in leadership and management. Thank you for attending this session. And then to the last part of our webinar, in order for you to register for our upcoming webinars, you are more than welcome to visit the EIT website. Under our news and events portion, you will be able to click on whichever webinar you're interested in attending. We actually have one tomorrow. It says predicting and preventing malfunctions, a revolutionary approach to the condition-based asset performance management. So you're more than welcome to attend that one as well. So for the certificate of attendance, kindly note that you will receive a digital certificate of attendance for participating in this webinar. So how to request for the certificate? This is really important, guys. If you could please make sure that you either click on the QR code, scan the QR code that is up on your screen, or you can use the link that is available on the screen as well. I'm going to attach the link or put the link in both the chat box as well as the Q&A box so that you guys are able to request for the link. Please make sure that you are completing the survey and inputting the information as to how you'd like your name to appear on the certificate of attendance. So the video and the slides will be mailed to your respective email addresses. These are the email addresses that you used to register for the webinar. So please give the team a couple of business days after the 19th of August. So the link To request for the certificate as well as the QR scan code is going to be available until Monday, 5 a.m. UTC time. Please note, I ask again, please note that if you do not request for your certificate using the link or the scan, you will not be able to receive the certificate of attendance. So utilize either the link or the QR scan in order to request for the certificate. Again, I'm going to leave the link to request for the certificate to the Microsoft form in the chat box and the Q&A box. Utilize either one that you are interested in using in order to request for your certificate. The link is valid until Monday, the 19th of August, 2024, 5 a.m. UTC time. Make sure that you get the time zone correct as well as the date. Failure to do so, unfortunately, we won't be able to provide you with the certificate. That's it for today. From my end, you are welcome to visit our website in order to request for any information regarding the courses that I've gone through. I will be sure to also leave my email address in the chat box as well as the Q&A section so that you guys can mail us regarding any questions you might have regarding the courses that EIT has on offer. As I said again, I'm going to leave the QR scan as well as the certificate link, request link up on the screen. I will insert them in the chat box as well as the Q&A box in order for you guys to utilize them. Thank you so much for attending. It was a pleasure being your moderator for the day. Please make sure that you take down either the link or the QR scan in order to request for the set. I'm going to insert them both in the chat and the Q&A section. Okay, just an example, this is how the survey looks. Please make sure that you complete this survey and make sure to submit at the end in order to request for your certificate. As I've said, I'm going to include the link in the chat box as well as the Q&A section so that you can request for the certificate. Guys, I'm going to leave the session for about 5 minutes more so that everyone is able to take either the QR code or the certificate link. It's also in the chat box and the Q&A section. Please utilize them. Thank you so much for your time. I hope to see you on another one. Goodbye.